Rates of change. So this is it, right? I mean, this is the last lesson of this unit, and then what is a test on Tuesday, but we'll be starting the new unit on Monday, and then there's a test on Tuesday. In room 302, right, which will be first period in the morning. I think. Is it? Yes. Yes?
Second. First period.
Well, you're writing first period. Your first period, your test is the first period Tuesday, right?
Yeah.
Okay. So anybody who gets extra time, check with me as to regards to how we're going to handle that, because just coming early would probably be the best bet, and we'll take it from there. Or if you have a spare afterward, life is even easier. The slope of a tangent can be viewed as a rate of change, since slope is the ratio of the change in y over the change in x. That is, slope is delta y over delta x. We say that slope is the rate of change. Oh my God, and over again we say this. In this investigation, we will look at other rates of change, starting with velocity. Suppose Sam drove to Edmonton, a distance of 300 kilometers in 3 hours. Although if we're talking velocity, it should probably be a displacement, shouldn't it? Oh, geez, I don't know who wrote this up. We can use the following formula to determine Sam's average velocity, the change in displacement. You guys, do you use S for displacement? I think you do, right? Yeah. Okay, so it's change in displacement over change in time, delta S over delta T. Our change in displacement, it would be 300 kilometers, and our change in time is 3, giving us 100 kilometers per hour. And I guess if we're driving to Edmonton, we should throw a north in there, but we're going to play fast and loose with this. So Sam's average velocity was 100 kilometers an hour. Does this mean Sam was consistently traveling at 100 kilometers an hour?
Absolutely.
Well, unless he can instantaneously get up. It's unlikely, right? Likely the speed varied, but his average speed, or average velocity really, was over a time interval of 3 hours. How do we determine his velocity at a given instant in time rather than over an interval of time? Doesn't this sound familiar to the problem of determining the slope of a tangent when we know only one point rather than an interval of change? Right. So we're looking really for the slope at that moment in time. What is the slope of the tangent? Example 1. The displacement of an object in meters is given by S is equal to f of t is equal to 5t squared, where t is the time in seconds. Complete the following table of values. Okay, so in 1 second, we will have gone, what, 5 meters, right? And in 2 seconds, how far? 20 meters. And in 3 seconds?
45.
Uh-huh. And in 4 seconds? 80. Yes. All right. And then I've sketched that out for us. There's y equals 5x squared, and here's our 4 seconds and our 80 and so on, right? Just if we were going to go back and look at that. Complete the following statement to determine the average velocity from time 1 to time 4. Okay, so in here, we're really looking then at the slope of this line, right? There's time 4, time 1. So the change in displacement is going to be f at 4 minus f at 1, or at minus 5, over 4 minus 1, which is 3.
Can you show that step fully? I'm not getting there.
Oh, so we're just taking them out of the table.
I was making a joke about 4 minus 1.
Oh, 4 minus 1. I guess I could. 20, it's Friday, right? Yeah, 25 meters per second. Okay, maybe you should come up here and work out B for us. So, or sorry, C. Determine the average velocity from t equals 1 to t equals 3, right? Okay, so we're just going to do the exact same thing, right? So we're going to write, it's the change in displacement over the change in time. Change in displacement will be f of 3 minus f of 1, negative 1, over 3 minus 1, which is, what was that for 3? Is that like 45? Yeah, so 45 minus 5 over 2, 40 over 2, or 20 meters per second. Okay, so we have a speed, average velocity of 20 meters per second. Now, what if we determine a simplified expression for the formula for the average velocity from t equals 1 to t equals 1 plus h? So we're just basically going to do the same thing yet again, right? So we're going to say, well, we want delta s over delta t, which is going to be f, but this time it's f of 1 plus h, right? It's not f of 4 or f of 3. It's going to be f of 1 plus h minus f of 1, so the distance over 1 plus h minus 1. So what's f at 1 plus h? Well, it's going to be 5 times 1 plus h quantity squared, right? 5t squared, but our t here is 1 plus h. Minus f of 1, and f of 1 is 5, over, what goes on the bottom here? H. Okay, did that all in one step. That's good. Okay, so what's that equal to? Well, it's 5 times, I guess we got to start heading down the page here. So what do we got? 1 plus 2h plus h squared minus 5 over h. So what do we got? We got a 5, all right, plus 10h plus 5h squared minus 5 over h. 5 minus 5. Let's write that as what? H 10 plus 5h over h. So we got 10 plus 5h. That's our that is our average velocity, right? Over the interval 1 plus h to from 1 to 1 plus h. Sorry. So determine the instantaneous velocity. So the instantaneous velocity is going to be what? Well, it's a limit, right? It's the limit as h goes to 0 of 10 plus 5h. Well, there's no reason we can't put h as 0 in here, right? It's not, I mean, having simplified the expression here, so that's just going to be 10 plus 5 times 0, which is 10 meters per second. So what does that tell us? The slope of the tangent line at a time of 1 second is 10. Okay, so that's the instantaneous velocity, the slope of the tangent line at t equals 1. In general, if an object moves according to an equation, s equals f of t, where s is the displacement, which is a directed distance, from the original position at time t, then s equals f of t is called the position function. Okay, so it's a position function, right? It's going to tell us where it is. the average velocity from time t equals a to t equals a plus h is given by, average velocity is the change in displacement over the change in time, is f of a plus h minus f of a over a plus h minus a, which simplifies to f of a plus h minus f of a over, Peter?
H.
Over h, right? And that's an average velocity. If we want the instantaneous velocity at time t equals a, denoted by v of a for velocity, is the what? The blank of the average velocity is h approaches 0. So it's the limit. Yeah, it's the limit of the average velocity as h approaches 0 and is given by, so v of a is the limit as delta t approaches 0 of delta s over delta t, okay, which can be written as the limit as h approaches 0 of f of a plus h minus f of a over h. Okay, so it's just the limit of the average velocity as the h value approaches 0, as you bring those points closer and closer together. Okay, and we saw that yesterday with GeoGebra, sliding that along, how the secant line is going to approach the tangent line. This means velocity at time t equals a is equal to the slope of the tangent to s equals f of t at t equals a. All right, so we're given a displacement, a position function, s equals t squared plus 2t, where t is the time in seconds. Determine the average velocity from t equals 3 to t equals 5. Okay, so what do we need? Well, delta s over delta t. The change in position is going to be s at 5 minus s at 3. S at 5 minus s at 3 over 5 minus 3. And we can substitute in, so what do we get? 5 squared plus 2 times 5 minus 3 squared plus 2 times 3 over 2. And then we can work these guys out. So what do we got? 25 and 10 is going to be 35. So 35 minus, and we've got 9 plus 6, 15 over 2. 20 over 2, or 10 meters per second. So that's our average velocity. Now, what was the velocity at 3 seconds then, right? Or what is the, so we want the instantaneous velocity, right? So we've got v at 3, which is equal to the limit as h approaches 0 of s of 3 plus h minus s of 3 over h. And I guess we're going to head across. Now we can head down. So the limit as h approaches 0 of, okay, so s of 3 plus h is going to be 3 plus h quantity squared plus 2 times 3 plus h. Okay, so that's s of 3 plus h, that's going to be our first term, minus s of 3, so minus 3 squared plus 2 times 3 all over h. Extend the page. Limit as h approaches 0. Okay, so what do we got? 3 plus h squared is going to be 9 plus 6h plus h squared plus, what do we got? 6 plus 2h minus 9 minus 9 minus 6 over h. Okay, so make sure that's all good. What do we got? Oh, so what do we got? We got 9 plus 6. We got a minus 9 minus 6. So we got 9 minus 9. We got plus 6 minus 6. Okay, what do we got? H squared plus 8h. Okay, so h squared plus 8h over h. Come across here. So we can factor an h out of the top. And then we can cancel our h's. And now we can put in h is 0, right? And we get the instantaneous velocity, which will be 8 meters per second. Okay. Questions about that? Concerns? Or stare at it a bit. Give you a chance. So in summary, in general, if y is a function of x, that is y equals f of x, then the average rate of change of y with respect to x at x equals a is given by delta y over delta x. It's f of a plus h minus f of a over a plus h minus a. And the instantaneous rate of change at x equals a is given by the limit as delta x approaches 0 of delta y over delta x, which is the limit as h approaches 0 of f of a plus h minus f of a over h. So it's not just speed, right? Sorry, velocity. It's not just velocity. It's not just change in position. Think about it. A spherical balloon is being inflated. Determine the rate of change of the surface area with respect to the radius when the radius is 8 centimeters. So if you think about blowing up a balloon, you know the surface area doesn't change at a constant rate, right? It's going to change at the bigger it gets, the bigger the surface area is going to get. And so we're asking, how is the surface area changing when the radius is 8 centimeters? Okay, so we're looking for an instantaneous rate of change, right? We're looking for the limit as h approaches 0 of s, in this case s for surface area, right, of 8 plus h minus s of 8 over h. And so we're going to use the function definition, right? Surface area change. So it's going to be 4 pi 8 plus h squared minus 4 pi 8 squared over h. All right, so 4 pi, that's just kind of a constant along for the ride, right? So let's factor that out. Limit as h approaches 0. So let's write down a 4 pi. And then we'll do the 8 plus h squared minus 8 squared over h. Okay, so we can expand this. Let's just go up here. Limit as h approaches 0 of 4 pi times. Okay, so squaring 8 plus h, what do we got? 64 plus 16h plus h squared minus 64 over h. So we got 64, we got minus 64. Got the h, we can now take the h out as a common factor. So we get 4 pi h and 16 plus h over h. And these guys cancel, giving us with the limit as h approaches 0 of 4 pi times 16 plus h, which will equal 4 pi times 16 plus 0 for 64 pi. And it's surface area changing as radius. So surface area is measured in square centimeters, right? So it's going to be 64 pi square centimeters per centimeter. Right? So at the rate, so the radius is changing in centimeters, right? So that's the bottom per centimeter. So 64 pi centimeters squared of surface area for every centimeter of radius at the point where the radius is 8 centimeters, right? And we can work this out for anything 7 centimeters, 6 centimeters, 5, and so on. Okay, rate of change, rates of change.